All right, and welcome back to Mr. Gregoris Math. Today we're taking a look at some initial value problems. Specifically, when we're given a derivative and a point that we know exists on the function, and we're asked to find the function itself. So remember, there's this relationship between functions and derivatives, right? And perhaps it's easy to sketch and show. So I've got the derivative sketched over here, 3x squared plus x. I just factored it and plotted the roots and knew it was a parabola that opened up. And you'd recall that we would draw the function by placing these lines that go down through the roots. And we knew that on these lines, at some point, the function had a slope of 0, which meant that there was an extrema. So there's either a maximum or a minimum. And then we did this thing where we analyzed the slopes. We said, okay, there's a positive slope here, so the function's sloping up. And there's a negative slope on this side, so the function's sloping down. So that must mean there's a maximum on this particular point. So we can just put a maximum arbitrarily. And that arbitrarily is a big term for what we're about to talk about. Then, as we got down to the minimum value of the derivative, we knew that somewhere along here, there was a point of inflection. And so with a point of inflection, it meant that the curvature changed. So we have something that has a maximum, so it's going to be concave down. And then the curvature is going to change. And then it's going to have a minimum. And then it's going to go back all the way up like this. We know it has a minimum because we'll have a negative slope on this side. And on this side, we have a positive slope. And so that looks like it's going to contain a minimum. So we'll go ahead and put a minimum somewhere down here. And I'll just sketch it in with pencil for now. And I'll change curvature as I get through my point of inflection and got tripped up by the paper underneath. And that's a fairly good sketch of what my function might look like. And I can just put a point obviously there. And it doesn't have to be at the intersection of the extrema. It could have been up higher. Perhaps I shouldn't have drawn it right at the intersection. But you may recall I talked about how this function is actually not anchored in space. It could be anywhere up or down and still have the same derivative that's drawn underneath. That's the whole point of this secondary point or this initial value. Once you have an initial value, then you can figure out where that function is anchored. Now, the reason why this initial value will help us with it is when we go ahead and solve for this, we're going to be left with a constant of integration. So remember, the relationship between a function and its derivative is that if you integrate the derivative, you should get back to the function. But of course, there's going to be this additional c value hanging around. And that's what the initial value is going to help sort out. And that c value is our constant of integration. So let's go ahead and substitute and try and figure out what f of x is. So the derivative of f of x is 3x squared plus x. Just leave this c out for a second. Now, I can do this term by term because it's a polynomial. So remember, I increase this power, so it goes from 2 to 3, and I divide. So I have 3x to the power 3 divided by 3. And for this term, I increase this power, which is a 1, and I divide. So this is going to be x to the power 2 divided by 2. And that constant of integration, well, I have to assume that there's a constant in here as well, and that is going to help to anchor whichever function I'm dealing with, whether it's the one that's drawn in here or the one that's drawn way up here. So I have to be very careful to ensure that I include this c. So there we go. I've got the function. I could simplify it a little bit by canceling out my 3's. And this is my prototype for f of x. But importantly, I know a value, and that value is going to allow me to solve for this last missing piece. So I'm going to be able to solve for c by using this value. So my x-coordinate is 1, and my y-coordinate is 3/2. So I'll have 3/2 is equal to 1 cubed plus 1 squared over 2 plus c. And 1 cubed is just 1. 1 squared is just 1, so I have 1 plus 1/2 plus c. And I think we're going to find out, actually, really quickly here, that c is going to be equal to 0 because 1 plus 1/2 is 3/2. And I have 3/2 is equal to 3/2 plus c. So subtracting from both sides, I get that c is equal to 0. This allows me to make the final statement that the function f is x squared or cubed plus x squared over 2. I don't have to write plus c anymore because I know plus c is 0. So let's go back to the diagram and see what that meant. Well, this function that I have drawn here is a cubic function, and it is a positive cubic function, and that's perfectly fine. But it has a y-intercept of 0, so mine currently doesn't. Mine currently has a y-intercept somewhere down here. So I actually have to take this function that goes from extrema to arrowhead, and I have to slide the whole thing up. So in sliding the whole thing up, I'll draw a better version. And actually the correct version. But what I want you to see is that they have the exact same features on the exact same x-coordinates. So my point of inflection is still along my point of inflection line. But because I now know what c is, that c is equal to 0, I know that my y-intercept is stuck there. So this is actually the correct function f, given we had f prime, and we know it went through the point 1 and 3 over 2, which would be probably somewhere up here. As you can see, this one clearly didn't go through 1 and 3 over 2 because it would maybe be at 1 and negative 3 over 2. So this initial point of 1 and 3 over 2 anchored my function in space. And that's how you solve an initial value problem. Best of luck, and join us next time on Mr. Gregoris Math. Don't forget to hit like, subscribe, and ring that notification bell.